So just for the video, you can see the solution to that last problem. It is 270 torr with only 2 sig figs. So now let's look at another problem of this type. All the problems we looked at so far, we were solving for one of the pressures. We tried those because the pressure is the most difficult because it's within that parentheses and you have to deal with it as part of the log term. But let's look at this one where instead of solving for pressure, this time we're solving for the enthalpy of vaporization. So calculate the heat of vaporization using the 2-point form of the Clausius-Clapeyron equation if the vapor pressure of the liquid doubled when we increase the temperature from 20 degrees to 40 degrees Celsius. What do we do first? Identify what we know. Okay? So we've got P1, T1, P2, and T2. So what do we know? Well, we know the original temperature is 20 degrees, which is 293.2 Kelvin, and my final temperature is 40 degrees, 313.2 Kelvin. What else do I know? It doubled. So what's P1? X, right? And what's P2? 2x. So if we think of it that way, fortunately, since we divide these, the x's will cancel and we can go ahead and solve, even though it appears we have too many variables. So we know the 2-point form, the natural log of P1 over P2 is equal to the enthalpy of vaporization divided by R times 1 over T2 minus 1 over T1. So again, once we've thought out the part of doubling the pressure, this isn't that difficult. Harrison? No, it's not negative because when I switched it to the 2-point form, I got rid of the negative sign here and switched these by kind of multiplying the whole thing by -1. So T2 is first, and that goes with the P1 that's first and on top. Otherwise, it would be. So we can go ahead and plug the numbers in. The natural log of P1, which we've called x, over 2x, P2, is equal to our unknown enthalpy of vaporization divided by R, 8.314 joules per mole Kelvin, times the reciprocal of the Kelvin temperatures, 1 over 313.2 Kelvin minus 1 over 293.2 Kelvin. So now we get x divided by 2x. The x's cancel, so we get 1/2. This is doubled, so we're going to get as many sig figs as we want. The natural log of 0.5 is equal to the enthalpy of vaporization over 8.314 joules per mole Kelvin times, this turned out to be a 0.003193 minus 0.003411, and when you subtract, preserving place, we get negative 0.000218. So this is the number I'll be using to multiply. So when I rearrange now, we have the natural log of 0.5 times 8.314 joules per mole Kelvin divided by a negative 0.000218 is equal to delta H. Now, when I did this, I just plugged in all the math and did the natural log and then multiplied across, and I got 26,100 joules per mole. And since it's got all those zeros hanging over there, I just reported the enthalpy change is 26.1 kilojoules per mole. I had 3 sig figs when I subtracted, preserving the place, so I can keep 3 sig figs in my answer. So that's kind of one of the harder problems because you sort of had to think through that P1, P2 thing. and you had to solve for the enthalpy of vaporization, which I think is easier because you only had to divide first and then take one logarithm. So you didn't have to deal with the log going backwards. I think it's a little bit easier. Okay, do you have any questions? Do you feel like you could do this once you know what the equation is and have it down in front of you, that you can do the algebra? Dwayne?
Does it have to be expressed in kilojoules per mole?
No, I just don't like to write all those zeros. Okay, I usually shorten it to not write in the zeros.
Will we be given the values of the gas constants or something?
Yes, the constants will be provided, but there's a lot of equations you have to remember. Sure.